The overhead, please. Hey, thank you very much. Okay, good afternoon, everybody. One initial reminder. This is the initial reminder. I will remind you 2 more times. This Thursday and next Tuesday and Thursday. Our midterm will be March 7 on a Friday, not on a Thursday, on a Friday. March 7, Friday, from 4 to 6 or 6 to 8. Your choice. But you need to let me know. You need to tell me, Professor, I want it to be from 4 to 6 or what? 6 to 8. So that I need just to make sure that I bring the appropriate papers to the number of papers to the exam. The room, I will tell you about it as soon as I get the assignment. I will tell you that. Clear? Can you guess why am I scheduling the exam on a Friday? No? 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 I don't want to waste a lecture. I don't want to waste a lecture. We have a lot to cover. You follow me or not? You will see we have a lot of stuff to cover. I don't want to waste any lecture on the midterm or something. So after the class, talk with me after the class. Not now. We need to start right now. Okay. Good afternoon, everybody. Let's continue our discussion from last time. We started looking at a quick review of RLC circuits, passive circuits. These are very important circuits. We will see that they are used as what? Resonators. They are also used as what? Match circuits and so on and so forth. So we need filters, bandpass filters, low-pass filters, and so on and so forth. So we said that we need to have a better look, or a short look at summarizing this. We started, first of all, looking at a what? A series RLC tank circuit. What is the major finding we saw? What is the major finding we saw last time? We saw that at resonance, the voltage across the inductor or across the what? Capacitor. Not across both. Across each one of them is much higher than the what? Than the voltage across the what? Across the resistor. By the way, how much is the voltage across the resistor? At resonance. What is the voltage across the resistor? The voltage across the resistor is what? Is Vin. Did you get this or not? The voltage across the inductor is a Q times as what? As high, and the same thing with the voltage across the what? Capacitor. But taking them collectively, the voltage across this is what? Is 0, because they will cancel each other. They are what? 90 degree? Oops. They are what? 180 degree out of phase from each other. The voltage across the L and the voltage across the C. Clear? We defined the Q, which is called the what? The quality factor of the circuit. We define it for the series circuit as either what? Omega naught L over R, omega naught L over R, or what? 1 over RC times what? Omega naught. Either you use this or you use that. You have to always remember that these two components can what? Store energy, whereas this one can only what? Dissipate energy or dissipate power. Did you get this or not? That will hold what? Electrical energy, whereas this one is going to what? It's going to hold magnetic energy. Did you get my point or not? Okay. For a parallel circuit, and easier to work with using what? The Norton's type rather than the what? The Thevenin's type. In here, what can you, by the way, in here, you cannot talk about what? Voltages. Why? Because all the components are connected in what? In parallel, which means they have the same what? They have the same voltage. Now answer me the following question. The current that at resonance, what is the impedance of these two? Not the admittance, but the impedance of these two at resonance. Infinity, which means what? This is an open circuit, yes or no? Which means all the current will come through what? Through R, yes? What is the current through the combination of these? The combination, 0. But the current through what? Each one of them is what? Q times as high as what? As the original current source. Did you understand what I just said or not? Q time. Not through the combination, but through each one of them. In other words, if you see the current in here, and if you see the current in here, if you calculate that, how do you calculate the current here? The current here is the what? Is the voltage divided by this impedance. Yes or no? Similarly here, you will see that it is what? Q times higher than what? Higher than the original current source. Agree? No response. Yes or no? But through the combination, what is the current? The current is 0 because the impedance is equal to what? Is equal to infinity. Clear? Now, again, as I told you last time, when you deal with parallel circuit, it is easier to use what? Admittances. So when we say an impedance is what? Open circuit, it means admittance is a what? It's a short circuit. Impedance and admittance, they are what? Inversely proportional. Clear? Clear? Okay. Now, when you do have this, again, as I told you, what did I tell you last time? The position of the what? In other words, where am I looking at the output voltage will determine what type of a what? What type of a filter is it? Are you following me? So, for example, if you look at what? If the resistor was in here and the capacitor was in here, then we discover that we do have a what? A band pass filter. Are you following me or not? If you put an inductor here, then you get a what? A high pass filter. If you put a capacitor here, you get a what? A low pass filter. Assuming you are looking at the output between these two terminals. Clear? Okay. Now, we looked at one of them, which was what? Oh, by the way, for the parallel circuit, the Q is the other way around from what? From the series. In the series, what was Q? Omega naught L over what? R. For the parallel, it's what? R over what? Omega naught L. In here, what is it? 1 over RC omega naught. In here, it's what? Omega naught RC. By the way, it's very easy to remember. Why? Because it's what? It's the inverse, the inverse of each other. Did you get this or not? Okay. Now, if this is equal to this, what did we get? We got omega naught is equal to what? What is the resonance frequency? This is the resonance frequency. What was it? Say that again. 1. I don't know what by means. I assume by means divided by. Okay, by. I don't buy. By means goodbye. LC. Clear? Clear? Oh, I'm so mean. Clear? That's what the resonance frequency. Notice, by the way, when I say resonance frequency, in what? In radians per second. Clear? Radian per second. This is, by the way, later on, we will refer to it as a what? As the tank circuit. This is going to be the load of the amplifiers. The what? For example, the LNA amplifier or the what? The power amplifier. That will be the load. We call it a tank circuit. Clear? Now, keep in mind, by the way, if there is no R in here, the circuit behaves as a what? As a resonator, an oscillator, at least theoretically. Did you get this or not? However, as we will see later on when we get to the oscillator design, we will see what? We will see actually this parasitic resistances or intrinsic resistances will result in what? Dying of the what? Of the oscillation. Clear? You need to what? You need to amplify it to sustain the what? To sustain the oscillation. Did you get this or not? But we'll get to that when we get to the oscillator shortly. We derived the what? We derived the impedance of this one, and we sketch the impedance, or you can also sketch the what? The frequency response. We saw the frequency response like this. What do you notice? As a Q is a measure of what? The selectivity of the filter, not the sensitivity, the selectivity of the filter. As a Q increases, the filter becomes what? Becomes more selective. And what does that imply? It implies that we need higher order of the filters. The filters become what? More complicated. Whether it's a Butterworth filter or whether it's a Chebyshev filter, you will take, anybody taking 541? No one? 541. Is he speaking about Butterworth, Chebyshev, and so on and so forth? These will be of what? Of the higher order filters. If you want to establish a Q, what? Q to be high. By the way, as a Q approaches infinity, the only frequency that you are passing is what? Is omega naught. Are you following me or not? The omega naught. That's the what? That's the ultimate you can get. Only omega naught you are passing. Okay. We defined also, we defined what? We defined the, if you look at this one, by the way, what do you notice? You notice no matter what Q is, the magnitude is still what? It's still the same. 1. Why? Because this is a passive filter. Cannot provide you with any what? Any gain. Yes? Is it possible that our filter provide me with a gain? That's an amplifier with a given what? Dynamic range? of the amplifier in the frequency domain. And the frequency domain means what? Throughout that range, it will provide you with what? Amplification. Clear? Okay. When it does not, then we defined what? We defined the values, this value and this value. When the magnitude fall to roughly what? 0.707. In the diagram it says 0.7, but in reality it's what? 1 over square root of 2. Remember, it's 1 over square root of 2 of the peak. Because the peak happens to be 1, then it's what? 0.707. If the peak is what? 5, then it will be what? 0.707 times what? 5, whatever that is, 0.35 something. Did you get this or not? From here to here, we refer to it as a what? As the 3 dB bandwidth. Notice, by the way, if you are getting the magnitude square, yes? No response. Yes? Then what will this one be? This one will be 1/2, which is what? 1 over square root of 2 square. This we call what? 3 dB below. Did you get this or not? Okay, good. Now, this is the bandwidth, the 3 dB bandwidth, and we found that Q is equal. From the equation, you can find it, omega naught divided by what? Divided by the bandwidth. Clear? Now, omega naught, by the way, is not exactly the midpoint between what? Omega 1 and what? Omega 2. It's the geometric mean rather than the what? Arithmetic mean. Clear? But it is close to each other. In other words, if you do it very, quick calculation and you see the midpoint, it's still close enough. Clear? So we say what? We say omega naught is the what? Is the geometric mean. Okay. And how do we get, one more time, how do we get to the omega 1 and the omega 2? We find the what? We find the point in which the magnitude response fall to what? 1 over square root of 2, or the magnitude square falls to what? 1/2. And you find omegas. And you will see, you will get what? 4 roots. 2 of them are on the positive side, 2 of them are on the what? Negative side. Did you get this or not? Of course, you only take the positive sides. And you will be able to tell which one is which. Why? Because the one greater than omega naught is the what? Is omega 2. One less than omega 1 is omega 1. Clear? The phase response, you can see, by the way, when Q, remember, for a system to be what? To be distortionless, which means what? Does not introduce any phase distortion. Question, what is a phase distortion? When we say phase distortion, what does that mean? In the time domain, what does it mean? Phase distortion. Phase distortion means the what? The pulse gets smeared. What does get smeared mean? Look at this. This is a pulse. Yes? Listen to me. If I get this is the input, and if I get the output here, listen to me. Was there a delay? But was there a smearing in the pulse? There was no smearing in the pulse. What does that imply? There was no what? Phase distortion. There was a constant delay. Every single frequency component at the input got delayed by the same what? Value. Did you understand that or not? However, if I get something like this, was there phase distortion? There was phase distortion. What does that mean? The pulse get what? Smeared. Do you understand what smear means? It's like as if one pushing the pulse this side, the other one is pushing it the other side. Now you might say, so what's the big deal? What is the big deal is that this decay will what? Interfere with the next symbol, which means this is what is referred to as what? The intersymbol what? Interference. You are interfering with yourself, not somebody else. Did you get my point or not? Because of this smearing. That happens when what? When the bandwidth of the filter is smaller than the bandwidth of the what? The signal. Did you understand what I just said? I want you to see this. I want you to see this and tell me. When Q is equal to 100, is that bandwidth narrow band or wide band? Narrow band, very narrow band. Did you get this or not? I want you to see the face. Is it linear? No, it's not linear. Remember, linear, it has to also pass through who? Pass through the origin. Did you get this or not? Yes or no? This one here. By the way, I want you to see Q equal to 0.5. Is it close to being linear? It's close to being linear. It passes through the origin, closer to be linear. Clear? In that case, the phase distortion is what? It's very little. Are you following me on that? Now, that is the reason, by the way, why we don't use channel select filter at the front end of our RF receiver. Why? We use what is known as what? Band select before the what? Channel select. Because if we use channel select at the beginning, that will result in what? A demand or a need for a high Q filter. Why a high Q? Because the channel is what? Is narrowband compared to what? Compared to the center frequency, to the carrier frequency. Clear? Okay, good. Now, this is, we talked about this already. Now, one more thing before we leave this one, which is the following. How do we model a lossy inductor or a lossy capacitor? A lossy inductor can be modeled by a series of what? R and S. No, R and what? L. Clear? Clear? Okay. So if we have a tank circuit, LC circuit, a tank circuit, in reality, what do we have? We have a capacitor in series, in parallel with a what? With an inductor plus a what? Resistor. Yes? Now, do you understand what the S stands for? This S is what? A series. Yes or no? Now, answer me the following question. Is this a parallel? Don't read. Yeah, read. Is this a parallel RLC or series RLC or neither? This neither. Do you understand that or not? Just because this one is parallel with this one does not make it similar to what? Similar to this guy. Similar to this guy. Did you get my point? Okay. But can we change it? Can we change it into a parallel or a what? A series. This is crucial, as we will see in just a second when we design the matching networks or the matching circuits. Did you get my point? Yes or no? I want you to help me. Let's see if you can help me. I want to change. Can you zoom in, please? There, thank you. I want to see, I have a what? What happened to the capacitor here? This is the circuit I have. RS, LS in parallel with what? C. I want to change it into this, which is what? Is this a parallel? This is a parallel RLC. What do I do? The impedance of this needs to be the same as the impedance looking in here. Did you get this or not? This capacitor, is the same as this capacitor. You agree? What is the impedance of this guy? The impedance of this guy is what? RS plus what? J omega LS. It's a terrible scanner here. RS plus what? J omega LS. Agree? What is the impedance of this guy? By the way, you notice now it's the P. P means what? Parallel. What is the impedance of this guy? Is what? Is this thing here. RP in parallel with what? J omega LP. Okay, myself, I cannot read it. Okay, so let's do this quickly. This is what? LS, this is RS, this is C, and I want to transform it into what? Into this. This is what? RP, and this is what? LP. So this is the same as this. Clear? What is the unknown? What are the unknown here? The unknown is RP and what? LP. What do? You find the impedance of this guy, which is what? Z equal to what? RS plus what? J omega LS. Did you get this or not? And it has a what? A real part and a what? An imaginary part. Then what do you do in here? You also find what? Z. Which is what? Help me. This is what? In parallel. And if they parallel, what is the impedance? R1 over R, sorry, R1, R2 divided by what? So give it to me. What is it? RP times what? J omega LP divided by what? RP plus what? J omega LP. Do we agree? Okay, and that's equal to what? Okay, can I multiply by the conjugate, divide by the conjugate? So what do I get? Give me the did I mess up? So what do I have? RP square plus what? Horizontal square. Yes? What do I have here? One second, let me write it. RP plus what? J omega LP. No, sorry. RP times what? J omega LP RP times what? RP minus J omega LP. Yes? The J with the J minus 1 with the minus. So what do I get? I get omega square, help me, LP square RP plus J omega LP RP RP, one second, RP square, I'm sorry, RP square. Yes or no? Then what do I do? What, by the way, how many unknowns do I have? 2 unknowns. How many equations do I have? 2 equations. What 2 equations? The real part and the what? Imaginary part. So what do I say? I say omega square LP square RP over RP square plus omega LP square is equal to what? RS, this is equation 1, and equation 2 is what? Omega LP RP square over what? Over RP square plus omega LP square is equal to what? Omega LS. Did you get it or not? Yes or no? Huh? I made a boo-boo?
What is the motivation of going from this circuit to the other circuit?
Can you wait a second when we get to the matching network? Here. Next set of charts. And I will show it to you all in detail. Can you be patient a little? Okay, good. The reason, by the way, is that so that we have a definition for the Q. This is not a pure series or a pure what? Parallel. We need a definition for the Q. And the Q is defined for what? For the series and for the parallel. But we'll get to that in a minute. How many equations do we have? How many unknowns? 2 unknowns. If you do that, you will end up with these equations. RP, you will end up with RP is equal to what? 1 plus Q square times what? RS, yes? And LP is equal to what? 1 plus Q square over Q square times what? LS. These in the midterm must be in your 8 by 11. Do you understand that or not? I don't want you to derive this in the midterm. You use this result. But I want you to see this result. What happened? The resistor got transformed to a what? To a much bigger resistor. Why? Because RS is multiplied. This one is negligible. Do you agree? So what do you have? RS multiplied by what? Q square. By the way, I'm assuming the Q is more than 1. Did you get this or not? Okay, RS. By the way, even if it is less than 1, this one is still bigger than this one. Because of what? Because of this one. Yes or no? Whereas the L did not change much. Do you understand it or not? The L is almost what? Almost the same. For high Q, 1 plus Q square over Q square is nothing. Clear? Okay. No response. Yes or no? Okay. Once you change it into here, can you find the resonance frequency? Once you change it into here, can you find the resonance frequency? What is the resonance frequency? It's what? 1 over what? Square root of CLP. It is not the same as what? 1 over the square root of what? CLS. But close. Do you agree that it's close? Why? Because the LS and the LP are close to each other. But it's not exactly the same value. Clear? So you can get, that's another reason, by the way, why we change it to parallel, so that we can get the what? We can get the resonance frequency of this RLC circuit. Clear? Okay. Can we do the other way around? This is, by the way, I just explained to you. RS is transformed to a what? Bigger RP. If Q is large, say Q is greater than pi, LP is approximately equal to LS. Now, how about the capacitor? Can we model it? A lossy capacitor. We do it the same way, but instead of what? Instead of, where is it? Here, sorry. Instead of what? If we do have the lossy, what will it be? Here. A lossy capacitor can be modeled as a parallel what? RC. Did you get this or not? A parallel RC. Now this will happen where? In other words, see the series? This is the series. If you do have a series tank circuit, is this a series tank circuit? But this one is not pure, so it becomes like this. Did you get this? But can I change the parallel now into series? I can change the parallel into what? Into series, which means what? It means I do the following. This, which is the parallel, I change it to what? The series. What is the unknown in this case? The unknown in this case is the what? Is the RS and the what? And the CS instead of the CP and the RP. Yes? Is it the same procedure? It's the same procedure. Yes? But now tell me what happened. The RP became what? When you change it to the series, it became what? Smaller. Did you understand that or not? The RS is smaller than RP. Did you get this or not? Whereas the capacitor is barely what? The capacitor is barely what? Changing. Why? Because it's Q square over what? 1 plus Q square. Clear? So what do we deduce from here? RP is always larger than what? RS. Whether it's from here or whether it's from what? Here. This is summary. This is what you need to make sure that is in your 8 by 11. Did you get this or not? RS is always larger than what? I said RS, I'm sorry. RP is also always larger than what? RS. XP is always larger than what? XS. Now, what does that imply? Imply, if it is an inductor, then it means what? LP is larger than what? LS. Why? Why? Because the X, what is the X, by the way? No, what is the X in words? The X is what? Is the impedance. Are you following me or not? But here we only have what? We only have the reactive element, which is either the inductor or the what? Capacitor. So if I tell you XP is greater than XS, what does it mean? J omega LP is greater than what? J omega LS, which means what? LP is greater than LS. Yes? What if it was a capacitor? 1 over J omega CP is greater than what? 1 over J, help me, omega CS, which means what? What does it imply? It implies CP is what? Less than CS, because you are going to convert. Clear? Clear? We are going to use these sets of equations so much, so I need you to understand it carefully. I would prefer that you write it on a separate paper so that you understand what I'm talking about. And this is the Q, and this is the Q for the what? For the parallel circuit and for the series circuit. Clear? Clear? Okay, good. Now, let's move on. All of this, by the way, you should have had it in 301. This is 301. It's linear system stuff. But I thought just to refresh your memory to review this. Okay, now, next. What am I going to use? I'm going to discuss the impedance, transformation, and what? Matching. Here, as we will see shortly, the transmission line itself can be used as a what? For matching purposes, for impedance matching purposes. But we have not discussed the transmission line yet. So when I posted this, I was debating, should I start with the transmission line or should I start with the matching network? Both of them will be included in the midterm anyway. The question is what? Is the question I felt that this one is better to start with. But when we get to the section of using the transmission line as a matching as an impedance matching circuit. I will delay this until we discuss the transmission line, and then we'll come back to it. Did you get this or not? Okay, good. Now, most important thing to the RF engineer is what? Is the matching network. There is an old saying that what? RF is all about matching. Look at this statement. RF is all about what? Matching. Clear? Okay. Now, let's understand why do we need matching before we get into the circuit. Why? Why? Matching. First of all, let's set it up. First of all, we have a load. This is a load. And then we do have a what? A matching circuit. And here we do have the what? The source. Clear? This is the load, ZL, and this is the source, Z what? S. And this is the matching network. Answer me the following question. How come I use ZL here? Is it possible that the load is what? Is the impedance is complex? What do you mean could be? Most of the time it is. We will see what? We will see when we talk about amplifiers. The input, did Aaron review a little bit of the CMOS for you? The MOS circuit? If you remember, which I doubt, but let's see if you remember, the input impedance of an amplifier, a common what? A common source amplifier is heavily capacitive. Yes or no? Which is what we refer to as what? CGS. CGS is the capacitance between the gate and the what? Source. It's heavily capacitive. Maybe there will be some what parasitic resistances in here. So I'm trying to tell you that this is in general a what? A ZL. Did you get this or not? Okay. And the question is what? Why do we need a matching? We want to match the load to the what? To the source. Why matching? The answer should not be why not. You need to elaborate a little bit. Clear? Oh, the first one, of course, which is the most obvious one, is the what? The power maximum. Power what? Transfer. We would like a maximum power transfer from the source to the what? To the load. Are you following me on that? Clear? Now, this is related also to the issue of the transmission line. We will see that the transmission line, if not matched properly at the load, there will be what? Reflection. Some of the power will be what? Reflected back. Are you following me on that? Cannot hear you. Do we want the power to be reflected back? Regardless of just the power losses, what does a reflection of a waveform back means? It means that it is going to be interfered with who? With the waveforms coming this way, resulting of what is known as what? Self-interference. Yes? And generating what is known as what? Ghosts. Do you understand what a ghost means? Ghost. What is the name of the ghost? The friendly ghost. Casper. You don't know Casper? Okay, anyway. A ghost means what? You have a picture and then you do have a what? A shaded version of the picture. The picture becomes what? Becomes as if it was, it has a shadow. Did you get this or not? That's from the reflection. We don't want that. We want minimal reflection, regardless of just the power losses, but we want what? Interference loss. So the first one is the maximum power transfer. We want that. Second, which is not very clear yet, unless we see it, we will see that to obtain the minimum noise figure, which is in what? In what system? I.e., for example, in the what? LNA. Yes? The optimum value, or the minimum value, if you'd like, depends on what? Depends on the source impedance. Do you understand that or not? This, I cannot show it to you right now unless we get into the analysis. Do you understand? But I want to remind you of it. If the source impedance that you have is not the one that generates the what? The optimum noise figure. Optimum noise figure is what? The smallest one. Yes or no? What do you need to do? What do you need to do? You need to use a what? A network transformer, an impedance transformer. I said a network transformer. An impedance transformer, yes or no? Or impedance matching circuit to what? To match or to transform RS to the what? To the desired RS. You lost me here. Did you lose me? You lost me. I can tell you lost me. You look weird. Okay. You are weird anyway, but you look weird. What is this RS? This is the source impedance or source resistance, whatever the case might be. Agree? This is not the one that generates the what? The minimum noise figure. Did you get this or not? So we have a device in here, which is the what? Which is, for example, the LNA. To obtain the minimum noise figure of this guy depends on what? We will see that it depends on what? The source resistor. But that source resistor is not the same as this one. By the way, if it is the same as this one, good, we don't need to do anything. Did you get my point or not? We don't need to do anything. Clear? But if it is not, then what does that mean? It means I need to use a what? The matching here? Yes or no? To get what? To get the impedance looking at here, the one that will what? The one that will minimize the noise figure from this guy. Did you get my point or not? Now, notice, by the way, that matching network, we would like it to be what? Lossless. Do you agree with this statement or not? Theoretically speaking, if we use an LC type circuit, will there be losses? There won't be losses. Why? Because an ideal LC circuit does not provide you with any losses. However, there is no such thing as a what? An ideal ALS. So we will see when you use matching circuit, one of the parameters that you need to take into account is what is known as the insertion loss. I don't want you to forget about this terminology. Insertion loss, every time you put a what? A circuit in there, a matching circuit, will increase the what? You need to calculate how much dB you are what? You are losing. Did you get this or not? Cannot hear you. Okay. So this is another reason for what? Another reason for this. And the third one, of course, is to minimize the what? The reflections in transmission line. 4. The 4, again, I cannot show it to you right now until we get to the detail. In the power amplifier, at the transmitter, the power amplifier, we wish to operate what? We wish to operate the power amplifier at maximum what? Efficiency. Did you get this or not? Operating the power amplifier at maximum efficiency results in the need that the voltage swing around what? Around the quiescent point. Did Aaron tell you what a quiescent point means? No, he did, but you did not attend the class. Don't tell me yes, he didn't. The quiescent point is the operating point. Yes? The swing around the what? The swing around the Q point should be what? Maximized. Do you understand that or not? And to be maximized, we need to make sure that we do have the right what? The right loading for the tank circuit. Did you get my point or not? Yes or no? Which means what? We might need what? We might need a matching network to achieve that. Clear? So this one to achieve what? To achieve maximum efficiency in power amplifier. We will get to this shortly, after the midterm. After the midterm, we'll get to this. Clear? Clear so far? A lot of stuff. And that is why the saying goes, RF is all about what? Matching. Are you following me? Transmission line, by the way, Z0 is equal to what? We'll talk about it in a minute. Z0 is like 50 ohm. Are you following me or not? But the output impedances of the previous devices or the input impedances of the what? Of the subsequent devices are in general what? Not 50. Did you get this or not? You need to design a what? A matching circuit. Every time there is a mismatch, you are going to lose what? You are going to lose power. You are going to increase the what? The noise levels and so on and so on. All of these things. Clear? Oh, let's see let's see if we can proceed from here. Did you get it or not? Okay, good. So impedance, again, as I told we will discuss all of these, matching the input to the LNA or the power amplifier to the 50 ohm transmission line. Where is that? The output of the power amplifier, when you connect it to the what antenna, do you need a transmission line? You need a transmission line. If there is a mismatch, what does it mean? There will be what? Reflection, which means the power is not going to be what? Radiated. Did you get this or not? Yes or no? Do you remember when we were talking about the link budget? I told you we need to include feeder losses in the link budget because there might be some what? There might be some mismatches in there. Clear? And that power will not be radiated. You cannot add it to the what? Transmission power or so on and so forth. Clear? No response. Clear? Okay. Now, where are we? 1 second. I lost. Okay. Now, why impedance matching? I just explained it to you. Now, let's see if you can help me derive the condition. By the way, the end result. Let's get to the end result before we look at the definitions. The end result is what? Is that if the impedance is a what? Is a complex impedance. Yes? So this is complex and this is complex. For a match, for the impedance match, I will show you in a minute that RS, what is RS? RS is the real part of this guy, needs to be the same as what? The real part of this guy, yes or no? And the imaginary part of this guy needs to be what? The complex, it should be what? The imaginary part should be the negative of the what? Of the imaginary part of this guy, yes or no? Which means what? It means that ZL has to be equal to what? ZS conjugate. Did you get this or not? We will prove this one in a minute. Yes or no? Okay. Now, if it happens to be real, then the equation is just simply what? RS equal to what? Equal to RF. Clear? Okay. Let's see if you can help me with the equations. What do I want? What is the goal? The goal is what? Maximum power transfer. Yes? Okay. So, and the maximum power transfer is when what? When the load matches with the what? So, what is the power? Let's see if you can help me. Where is the 1/2 coming from? This one is the what? Is the RMS. Are you following on? That's a sinusoidal. Yes or no? Vn. Where is the Vn? This is the power delivered to the load. Yes? This is the power delivered to the load. What is it? It's 1/2 Vn square. Vn is the voltage here. Yes or no? Okay. Times what? The real part of 1/ZL. Why is it the real part? Why? The imaginary part is not going to dissipate. It is not going to dissipate any power. Did you get this or not? The real part. Okay. Which is what? Which is 1/2. Now, what is the Vn? The Vn is Zn divided by what? The total. Yes or no? What is it? It's the absolute value. Why absolute value? One more time. Why is it absolute value? We are measuring the what? The power. The phases does not get into the picture. Yes or no? The phases does not have any effect on the what? On the power calculation. So it's the what? Absolute value of ZL over ZS plus ZL, the absolute square times the real value of that. Clear? Instead of the ZS and the ZL, substitute what? RS plus JXS, and ZL is what? RL plus what? JXL. Did you get this or not? Okay, by the way, remember, XL, if it is negative, then what does it mean? It means that this is a capacitive element. If it is positive, then it means what? It's an inductive element. Did you get this or not? Okay, so replace this ZS by what? RS plus JXS, ZL, RL plus JXL. Clear? Group the resistance together. Group the resistance together. Take the what? Square of the real. Square the imaginary, square, because this one, yes or no? The real part of this is just what? RL, yes? And if you get this is the power. What do you do to the power? What do you do to the power? I'm still waiting. You need to what? You need to take the derivative, partial derivative of P with respect to what? RL, and you equate to 0, and you need to take the partial derivative of P with respect to what? XL, and you equate it to 0. Why? Why are you doing this? We want to get what? What is the value of RL and XL that results in maximum power transfer? Did you get this or not? Cannot hear you. Let me ask you a question. Is maximum power transfer and maximum voltage transfer the same thing? Yes or no? It's no. Why? Maximum voltage transfer, what should the load be? Open. Somebody said open. Who said open? Hey, that's correct. It should be open. Because if it is open, what is the voltage at the output? The voltage at the output is the same as the voltage of the source. Did you lose me? Did you lose me? Whereas the power, maximum power transfer is when what? When there is a matching between the what? Between the load impedance and the source impedance. Can you hold your question 1 minute? Let me show you this. Okay. So what do we get from here? What do we get from this equation? 2 equations. How many unknowns? 2 unknowns. We get, if you find this, you get this equation. Now, when you take this equation and substitute it back in the what? In this equation, what are you getting? You are getting this equation, which is what? P equal to what? Vs square over what? 8RS. Did you answer where the 8RS came from? Okay. Will this one cancel? This one cancel. This one will what? Double. Square 4. 2. That's 8. Did you get this or not? And this RL is the same as RS. Yes? So what do you do? You cancel with this one, you get 8RS. This is the maximum what? The maximum power transfer from the what? Source to the what? To the load. Clear? Question.
Yeah, what does taking the partial derivative here mean? What does it mean?
No, but taking partial derivative is that if you do have 2 unknowns and you want to optimize with respect to these 2 unknowns, when you take the partial derivative, for example, with respect to RL, you keep XL what? Fixed. Did you get my point or not? Did you get?
We equate it to 0.
Unless you want to maximize it, the slope is equal to what? 0. Notice, by the way, when it's equal to 0, in reality, you need to take the second derivative to prove whether it's a what? Whether it's a maximum or whether it's a what? Minimum. See, when you have this, slope is what? 0. Slope 0. Both of them, the slope is 0. So you need to look at the second derivative. If the second derivative is negative, then what is it? It's a maximum point. If it is positive, then it's a what? It's a minimum point. Take my word for it. It's maximum. Take my word for it. I don't want to go and to prove this for you. Take my word for it. You have no choice. You need to take what? You need to take you need to take the derivative and you equate it equal to 0. Clear? No response. Clear? Okay. So the maximum, if the load happens to be a what? If the load happens to be a what? A real load, then RP is equal to what? RL is supposed to be equal to what? RS. Clear? No response. Clear? Okay, good. Now, let's get to see how do we do the transformation. From what? From one resistance to another resistance. At the beginning, listen to me. At the beginning, we are going to assume that both the source and the load are what? Are purely resistive. However, the load and the source, they don't need to be what? Resistive. Then what do? When we include the non-resistive part, we will lump it with the what? With the matching network that we generated. Did you lose me? You lost me. Let me explain to you a little bit, just a little bit. You see, let's assume that the load is like this, which means what? It's a series of resistance with what? With inductor. Did you understand that or not? Ignore this. Ignore it totally. Remove it. You follow me or not? Design the what? The matching network. Now let's assume the matching network is of the L type. I will show you what L type means. Is this a L type? This is called the L transformer. Yes or no? Let's assume this is 5 Henry. Just an example. These are numbers. And let's assume this is what? 1 Henry. Omit this first. Use the what? Matching of what? Resistive load. And then what do you do to this? Lump it with what? With this guy. Did you get my point? Yes. Which means what? It means that as if now this is the matching circuit. Which one is this? 6. Did you get my point or not? Yes or no? It's similar to the capacitors also. But keep in mind, if the capacitors are in series, you don't what? Sum them in series. You do understand that, right? If they are in parallel, you what? Sum them. But if they are in series, you need to what? Sum them as if they were resistances in parallel. Yes or no? So I don't want the case in which the load is what? Complex bother you. Ignore the complex part. Solve the problem, match it, and then what? Incorporate the imaginary part of the load into your what? Into your matching network that you are designing. Clear? Okay, good. Now, let's see.
How come incorporating the inductors that I neglected will not affect my matching circuit?
The matching was based on what? Was based on a pure resistive load. It was not matched. It was not based on what? An inductive matching. So when I get a what? A certain what? A certain resistance. A certain inductor. I can just simply what? Lump it with the other one, which it will not have any effect on what? On the transformation. By the way, I will show you that. Your question is premature. Can you be patient a little bit? We have not even talked about the L match yet. Can you be patient? Okay, good. I will get to all of these in just a second. By the way, the TA also will introduce you, although I'm sure you already know that. Are you familiar with the Smith chart? Yes. How many of you is not familiar with the Smith chart? He will introduce you to it, and if you feel comfortable using it in the midterm, I will bring with me a whole bunch of what? Smith chart. But I'm not going to go over it in class. You must have had it before, so I will give it to the TA. If you are familiar with the Smith chart, feel free to use it in the midterm. If not, you are stuck with what? Equations. Did you get my point or not? Okay, good. Now, let's understand the first what? The first matching device. The first matching device is a transformer. Is a transformer where we do have the what? The primary coil and the what? Secondary coil. Now, let's see if you can help me with this. What is V2? This is the what? The V2, and this one is the what? Is the V1. The ratio of the turns is what? 1 to what? N. Yes? Now, 1 to N, what does it mean? It means V2 is greater than what? V1. By what ratio? N V1. Are you following me or not? The current, on the other hand, is the what? Is the opposite. Did you get this or not? So it's I2 equal to what? 1 over N times what? I1. Yes or no? Now, if you write this equation, what is the power, by the way? What is the power? Is V2 times I2, which is what? NV1 times what? 1 over N I1. Are you losing me? Did we get the same input power? Why? There is no losses here. I'm assuming that it is an ideal what? Transformer. Are you following me? There is a what? There is a steady state flow of the power from the input to the what? To the output. Did you get this or not? From these equations, what do we have? What do we have? We are going, by the way, notice the ideal transformer has a voltage or a current gain, but has no what? Power gain. I need you to understand. Did you understand what this means? Yes. Is there a voltage gain? Yes. There's a voltage gain. Yes or no? Is there a what? Is there a current gain? No. Why not? If you, instead of 1 to N, you put what? N to 1, you will have a what? Current gain. Did you understand what I just said or not? It depends on which side has the more what? It's more turns. Did you get this or not? But the power gain is always what? Is always 1 because they balance it out. There is no losses in there. Did you get this or not? Now, what is I2? I2 is V2 over what? Z2. This is the load here. Yes? I1 is what? NI2. This. Now, what is the impedance looking this way? The impedance looking this way is what? Is Zn. Yes or no? And what did we get? The result that we get is, where is it? Where is the result between Zn and Z2? Zn. This scanner is terrible. Zn is equal to what? Z2 over what? N squared. Clear? No response. Clear? Okay. I want you to tell me what is the problem with this circuit using a transformer. Using a transformer. These, the number of turns, the N to 1, needs to be what? In other words, listen to me. Let's assume that you were given Z2. See, what does this one tell you? It tells you Z2 over Zn should be equal to what? N squared. Did you get this or not? Which means what? It means the only thing that you have control of is what? To achieve matching between Z2. Why do we call it Z2? This Z2 is ZL. Yes or no? Why? To match. What is the thing that you control to what? To provide for matching between Z2 and Zn. It's the number of coils. It's the number of turns. Yes or no? That number of turns, it needs to be what? Integer. Are you following me or not? So you can only what? Approximate for some values. Did you get my point or not? Yes or no? You can only approximate for some value. But we will talk about that when we get there. But did you understand it? Yes or no? Okay, good. Now, next type of matching circuit. Next type of matching circuit is called what? LC network. LC network. Now, we will be calling it the what? The L match. There is an L match. This is an L match. Does it look like an L? Okay. And there is a what? What does it look like? A pi, a T. Are you following me or not? Pi, T, L, but we'll start with the L. Clear? Okay. Now, the LC networks as impedance transform. Now, recall from what? The previous set of charts, the one we just finished. Recall that we can replace any series RC or RL. Where is the set of charts that I told you to always... one second. This one. This one. Let's keep it because we are going to need it. If we can replace any series RC or what? RL with a what? With a parallel RC or what? RL. And vice versa. Clear? During this transformation, what did we see? We see that the series resistance was transformed into a what? A larger RP or what? Vice versa. What does vice versa mean? Means RP is transformed to what? A smaller RS. Remember one more time. RP is always larger than what? RS. Which means what? It means that you can what? Match an RP to a smaller RS or what? Match a smaller what? To a what? Larger RP. Did you get this or not? I want you, first of all, before we get into the detail, I want you to understand the notation. Do you understand what this means? These notations. This is the L match, for example. What does it mean? This one means what? Low to what? High. Low to what? High. Did you get this or not? What is this? By the way, this is a T match, which is a what? Which is an L match back to back. Did you get this or not? What is this? Low to what? High. This is like similar to this, but this one will be what? High to low. Did you get this or not? What does this mean? This is a pi match. This one is what? High to low, low to what? High. Did you get this or not? Yes or no? And we'll get to that in just a second. So the LC network can be used for what? Can be used to map a what? A smaller resistance to a what? Higher resistance, or what? Vice versa, which I'll show in just a second. Yes or no? Okay. LC networks are used for impedance matching for narrowband systems. Why? Why? The Q factor, we just saw the Q factor is that you are going to get what? You are going, when you are looking at a resonance, are you following or not? You are going to get what? You are going to get the bandwidth is much smaller compared to the what? Compared to the Q. Do you understand it or not? Remember, the resonance will appear at how many frequencies? One frequency, which means what? It means the matching will be what? The matching will be done only at what? At one frequency. Any other frequency, the matching will not be what? Will not be perfect. Did you get this point or not? You lost me. I think you lost me. But we'll get to it in a minute. We'll get to it in a minute. Yes or no? Okay, good. Now, let's see the L match. Let's see if you can help me here. What do I have? I have a resistor, which is RP. Yes? I want to match it to a what? I want to transform the impedance RP to a what? To a lower impedance, RS, which means what? Help me. I have a what? An RP, I want to match it to a what? A lower impedance, RS. Yes? Let's see if you can help me. This is RP. I'm going to put what? I'm going to put an inductive element. I said inductive, sorry. A reactive element. You notice I said reactive element? It could be a capacitor or it could be a what? An inductor, depending on whether XP is what? Positive or negative. I will put it in what? In parallel with the RP. Yes or no? And then what will I do? I transform this into a series, which is what? RS JXS. Yes or no? And then I will add in series the complex conjugate of this guy. Yes or no? So that they cancel and I end up with what? RP. Did you get my point? Yeah, sorry, I get the RS, sorry. I get the RS on this side. Did you lose me? You lost me. Okay, concentrate, please concentrate. I have RP, this is the RP. I want to match it to what? RS. And RS is what? Smaller than RP. Smaller than RP. Agree? What am I going to do? I'm going to put a reactive element in parallel. I call it what? JXP. I then transform this into a series. Yes or no? RS, JXS. And then I will add the complex conjugate of this guy so that this cancels with this. And I end up with what? Just this. Yes? So where is this? This now the overall network. Where is this guy? This guy is this guy. One second. Yeah, this guy is this guy. Yes? Where is this guy? There's a typo here. Where is the typo? This one should be minus JXS. Clear? Clear? Which means the L shape is which side? This side. I want you to see the L shape here. This is the same as this. You go what? High to what? Low. The L will be what? Pointing towards the source. Did you get this or not? Okay. Could it be this? Could it be this? Yes or no? But they need to be what? If this is what? JXP, this one needs to be what? Minus JXS. What does that mean? If this is a capacitor, inductor, and vice versa. Yes or no? I get this. I will show you the numerical example in just a second. Or this. If the L is pointing toward this side. Yes or no? What is the impedance looking here? Here, this way. It's just RS. Did you understand that or not? Impedance looking here is what? Is RS. Yes? Why do I call this one a high-pass filter? A high-pass L match. Why do I call, which one to choose? Do I choose this or do I choose that? Or does it depend what the application is? Depends. Why do I call this one high-pass? A high-pass because what? The capacitor at high frequencies is acting as a what? Short circuit. Yes? It is blocking the what? DC. Are you following? So if I want DC coupling, sorry, DC blocking. DC blocking means what? AC coupling. Did you get this or not? Yes. I will use this. Whereas this one is what? This one is a low pass filter. Are you following or not? Yes or no? For AC, what is this? For DC, sorry, for DC, what is this impedance? Open, which means what? DC will come in here. That's a DC coupling. Did you get this or not? Okay. Now, let's see if you can help me. Numerical example. I want to transfer 50 ohm to what? 5 ohm. This is 50 ohm, and I want what? 5 ohm. Let's see if you recognize these equations. This, I want to change it to this. So it's this to this. What is the Q? What is the Q? Tell me what is the Q here. It's RP over RS minus 1, the square root. Did you understand where this came from? No response. Okay. Where is this came from? Here, here. This one. This one is this one. Yes or no? No response. Why is this one XS? This CS is what? 1 over what? This XS, sorry, XS is what? 1 over what? J omega CS. So the CS is in the denominator. Did you get this or not? No response. Okay, finally, where did this come from? XP is equal to what? RP over what? Over Q. That's the definition of what? That's the definition of the Q for the parallel circuit. Yes or no? If XP happens to be what? Inductive, then what is the Q? It's R divided by what? Omega naught L. Yes or no? If XP happens to be what? Capacitive, then the Q is what? RP times what? J omega, the omega naught C. Did you get this or not? Okay. So you understood this equation? You plug it in the equation. What do I have? The Q is what? RP over RS minus 1, which is equal to what? 3. Yes or no? You take this Q and substitute it here to find what? LP. Yes, XP, by the way. When you find XP, then you can find what? LP. Clear? And then you find what? You plug it in here to find what? CS. Clear? No response. Clear? No response. Okay. Now, let me ask a question. By the way, is it the same thing here? It's the same thing, but it's the other way around. Are you following me or not? And instead of capacitive is what? Inductive, and instead of inductor, capacitive. What is the problem with this design? What is the problem with this design? The problem with this design is that you have only a single what? A single level of freedom. Which means what? If you know RP and RS, everything will depend on the value of what? Q. So if you find the Q and you plug it in these two equations, and you found the values of the L and the C not practical, you are stuck. I lost you? Did I lose you? The RP and RS are given in the problem. You follow me or not? Which means what? What does that fix? Fix the Q. And if the Q is fixed, then it means what? Whatever you get for the LP, yes? Or the what? CS. Let me ask you a question. What is this? When it says 1 gigahertz, it says transfer 50 ohm to what? 5 ohm at what? 1 gigahertz. What does it mean? Just one frequency, the matching is going to what? Work. If the frequency deviate a little bit from what? 1 gigahertz, the matching will not be what? Perfect. And that's what it meant a moment ago when we say the LC is a what? Is a narrow band matching network. Do you understand or not? Yes or no? Clear? Okay, good. So, this 1 gig, by the way, what is this 1 gigahertz? That's the RF frequency. That's the resonance, if you would like. That's the center frequency. Did you get this or not? And if there's a deviation among this, that's why, by the way, we would like our oscillator to be close to a what? A pure oscillator, which means what? I'm going to get an impulse if I look at the spectrum analyzer for that oscillator. Otherwise, this one will not be a true matching network. Clear? Okay. Now, did you understand the analysis? Analysis. Tell me now, what is the other way around? Now, suppose we want to transform an impedance, which is what? RS into a bigger what? RP. This one is what? What did we transform? We transformed RP to a what? Lower. In here, we want to transfer a smaller to what? Higher. What do? I put what? I put a series. Here, what did I put? I put a what? A parallel. Here, what do I put? A series. Then what do? I replace this by its equivalent, parallel. Yes or no? Then I put a what? A parallel, which is the complex conjugate of this guy, such that this one with this one, the admittances will what? Cancel each other, and what do I end up with? RP. Yes? So what is the network? The network consists of what? This, which is in series, yes or no? And this, which is this guy. Did you lose me? Did you lose me? This, in series, JXS, and this, which is in parallel. And again, you can see one of them is XS, the other one is what? Minus XP. Yes? Could this one be capacitor? This one will be what? And vice versa. And the L is pointing toward what? The L is pointing toward the what? The lower resistance. How about this one? Where is the L pointing toward? The lower resistance. So the L is always pointing toward what? The lower resistance. Whether the lower resistance happens to be at the source or at the what? At the load. Did you get this or not? Let's see if you can help me. By the way, are these equations the same equations? But which one am I using? Instead of what? Instead of this set of equations, I'm using what? This set of equations. Did you get it or not? Yes or no? Same thing. Or, by the way, will the Q change? Will the Q change? The Q will still be what? By the way, you know that the Q has to be there. Why? Sorry, has to be this way. Because if it is RS over RP, you made a boo-boo. Why? You are going to get square root of what? Negative sub. That's imaginary. Did you get my point on that? Yes or no? Okay. Is it the same problem that we just talked about, which is what? You have only control over who? The value of Q by what? By whatever is given. Whatever the values are given for RP and RS. Yes? Once you choose Q, once you choose Q, then you are what? And then you are stuck with the values of what? Of the L and C. And if they happen to be of values, which is what? Out of the ordinary, big, for example, big inductor. Are you following me on that? Then you are stuck with it. Clear? Okay.
Professor, we have 5 minutes left.
Thank you. Do I need to go through a numerical example of this, or did you get it? Exactly similar to the previous one. Okay, before I get to this, I need you to understand. What is this? This L is what? Is this way. So this is what? High, low. What is this? Low, high. Why? Because the L is always pointing toward the what? The L is always pointing toward the what? The lower resistance. So what do we have here? High, low, low, high. Yes? How about this one? Low, high, high, low. Low, high, low, high. Yes? Question. Why do we go into these types of matching networks? What was the problem with the L? One more time. In a single L match network, the Q factor and the bandwidth of the matching networks is determined by the impedance transformation factor. What is the impedance transformation factor? What is that? That's the ratio of RP over RS. So the value of the Q and the bandwidth of the matching network is determined by what? Is determined by, why the bandwidth, by the way? Why the bandwidth? Why is the bandwidth determined by the impedance transformation factor? The bandwidth is equal to what? Omega naught over what? Oh, sorry. The bandwidth is equal to, help me, omega naught over Q. Omega naught is given. Omega naught is specified in the problem. So by changing Q, by finding Q, you find the what? The bandwidth. You have no control over it. There is no degree of what? Freedom in choosing the component values. There could be some cases where the bandwidth is not acceptable or the component's values are what? It's not practical. Did you get this or not? Yes or no? Okay. One possible solution is to what? Cascade multiple L matches or create what is known as what? The T match or the what? And the pi match. Why? Because now you have what? You have, in here you don't have any what? You don't have any degree of freedoms. In here you will have degree of what? Freedom. You could choose the intermediate resistance. Do you understand what intermediate resistance means? Concentrate. Here, what do I want? I want to match this to this. Could I choose the middle one? Could I choose the middle one? That's a freedom of choice. That's a degree of a freedom. Did you get my point or not? Yes or no? Okay. Let's see if one example. I'm running out of time here, but let's see if you can help me here. This is, what is this? This one, this one. What is this, by the way? High, low, high, low. No, I said it wrong. It's one more time. I messed up. Low, high, low, high. Yes? If I say, once you say something wrong, you have a feeling you messed up. Feeling, inside feeling, you messed up. Okay, help me here. This is the RP. Yes? RP, by the way, is greater than RS. But I have a what? A degree of freedom in choosing what? RI. Which is what? In other words, this is going to map it to what? Match it to what? RI. And the RI will match it to who? RP. Did you get this or not? So by this RI is not given in the problem. Do you agree? What is given in the problem? RS and RP. This, you can choose it. So that you can choose it such that the components become what? Reasonable. The bandwidth becomes reasonable and the what? And the components, the values of the components becomes reasonable. Clear? No response. Okay, by the way, what is this? What are you combining? You are combining a high-pass filter with a what? Low-pass filter. Yes? What do you get? You get a band-pass filter. Did you get this or not? You get a band-pass filter. Yes or no? Okay, good. Now, what is the equation? Let's see if you equation. I will run out of time, but let me try anyway. Okay, what is the RI? RI is going to be what? The summation is the what? Is the geometric mean of what? RP and what? RS. Did you get this or not? This is a value I got. Now, what is the QI? Now we have two Qs. One on the what? Left. The other one is on the what? Right. Because we have two equations. Oh, sorry, two circuits. This is the Q on the what? On the left. This is the Q on the what? Right. Did you get this or not? One of them will handle this side. The other one will handle what? That side. Did you get this or not? Okay, but I don't want to go too fast on this. I think I ran out of time. Did I run out of time?
Yes, Professor.
Okay. I will show you this. I will write it on another piece of paper. This one is not very clear. But did you get the idea of introducing another degree of freedom by choosing the what? By choosing the by choosing the middle resistance. But I will show it to you next time.
This concludes today's session of EE 544 on Tuesday, February 25th, 2014.